Record. Okay. All right. So after talking about sampling, what we can do about different things, we are getting one step closer, I think, to test hypothesis or making inference. Okay. So the inference that we talked about earlier is that we're trying to use sample statistic, right, to make inference about the unknown but fixed parameter of the population. Okay. And now we're moving to topic 13. We call it assessing models. Okay, so this might sound nothing like what we have seen before, but you will see that everything that we mean by model, okay, is really just a set of assumptions about the data. Okay, and what we are trying to cover in this topic is that how we can use different ways to assess whether a model, which is a set of assumptions about the data, whether it's good or not. Okay. In data science, many models involve assumptions about process that also involve randomness. That's why we call them as chance models. Okay. So just like the chance that we talked about earlier as well. Okay. So we will see in this case that there could be many different models about how the data are, like assumptions are made about the data, how they are generated, stuff like that, or any kind of things that you might want to test about. Okay, so for us, we want to talk about some general approach through Python, as you will see again, of how to how to assess this kind of models in general. Okay, so we're also going to bring back what we have covered so far about the repeated sampling and all of the sampling distributions and different stuff that we have talked about so far. Okay, so approach to assessment here. Okay, so again, the model, okay, maybe with some kind of assumptions, we're going to talk about a few examples soon. Okay, the general approach that we're taking over here is that, well, if we have a model, like let's just say somebody gives us a model, which is a set of assumptions. Okay, if we are able to simulate data using Python in particular, according to the assumptions that the model has made, then we can learn about what the model is going to predict. Okay, so this is saying that, well, you might have different models, maybe model A, model B. If I'm able to generate data from these two different models, and maybe I can check which one is better by checking this, how similar or how resembling the simulated data from the two different models to the actual data that I'm seeing. Okay, so that's intuitive, hopefully for you all, that's an intuitive way to think about what we can assess a model, whether a model is good or not. Okay, so the next step, like we just talked about as well, is that we're going to compare the predictions to the data that we observed. Okay, if the data and the model's predictions are not consistent, then that could be some evidence against the model. Okay, so again, I'm using the model in a very vague way at this point. Okay, so please bear with me. We're going to go over two examples in this topic that we're going to have a specific model set up. Okay, and then we're going to see how we can generate or simulate data according to the model assumptions. And then we actually also have the observed data, so we can compare against the observed data to see which one, or I should say, to see if there is any evidence against the model because maybe the data, the observed data and the model predictions are not consistent. Okay, so the first example is what we call jury selection. Okay, this is actually a historical event. Okay, Swain versus Alabama in 1965. Okay, so this is a particular county, Alabama, where Robert Swain, an African-American man, was convicted of crime. Okay, he reappealed. Okay, because notice that later on, they noticed that in the jury, 12 people, all of them are white. Okay, so they're saying that, well, there might be some bias going on. So one way we can check, okay, is that here in that county, 26% of the population were Black. Okay, and here of a 12-person jury, oh, sorry, here. Okay, it's 100. Sorry about that. It's 100 back then. In this case, the jury panel actually consisted of 100 men. Okay, all of them are over 21 years old. Okay, and the question now becomes, okay, so if they say there's no bias going on, okay, that's actually a model, right? They say there is no bias going on. Then what we will see is whether for a 26% of the population were Black, for that kind of population breakdown, how possible it is that you're going to actually have 100 men on the jury, all of them are white. Okay, so this is, even though it's just like, if you look at those terms, it might not be easy to decipher which one was the model really going on. Okay, but just like I said, actually, let me actually just, oh, sorry about that. Okay, 8 men on the panel were black out of 100. Sorry about that. Okay, so, okay, let me recap this really quick. Okay, so for this particular case, okay, 8 men out of 100 men, okay, were black. Whereas in the population, 26% of the population were black. Okay, so our question is that, well, the data, the observed data is 8 men out of 100 men are black. Okay, but the model that we know, if there's no real bias going on about the jury selection at all, then on average, 26% of the jury, right, should be black. Okay, because it should be representing what the population racial breakdown was. Okay, so this is, like I said, the data that we observed is 8 men on the panel were black out of 100 men. Okay, the model, what the model is saying that if there's no bias, then 26% of the population black, then you will be on average observe 26 out of 100 men to be black, right, on this jury. Okay, so back then, the Supreme Court ruling was actually against this appeal. Okay, it denied the appeal. Okay, but now we are probably able to use what we have learned so far about the model, and then about how we can generate a large number of data sets to see if this is making sense. Okay. So sampling from a distribution that we know, okay, so we have seen how to do sampling from a numerical distribution in the past, like uniform random sample before, okay. Now we have to introduce something new, what we call sample at random from a categorical distribution. Because if you look at the model here, okay, it's 26% of the population were black. Okay, so it is 26% versus 1 minus 26%, because that's the breakdown, right, of the black and white racial breakdown. And then we're going to use that to sample a jury selection every time. Okay, so it is a categorical distribution because you have 2 categories, right? It's not a numerical variable. It's whether it's black or not black, or white versus white, black versus white over there. So we're going to use this particular command. So I'm going to highlight this before we go to the breakout, before we go to the demo. We're going to use what we call sample underscore proportions. Okay, so this is a function that we are able to sample from a particular population distribution, from a particular sample size that we want, and then replicating the population distribution over here. Okay, so you have 2 inputs, okay, the sample size, okay, that's how many you want to do, okay, and the pop underscore distribution is the breakdown that you know in the model. Okay, so just brainstorm really quick over here. If I have a jury of 100 men that I'm going to sample, right, so my sample size is going to be 100, okay, because I'm trying to replicate a jury selection. And the population distribution over here, I think will be 26% versus, in this case, 74%, right? Because I have the model, which is what we call like population distribution over here, because in the population of that county, 26% of the men, 26% are black. So the breakdown of 26 and 1 minus 26%, which is 0.26 and 0.74, that will be the categorical, like the list of probabilities I'm actually generating from the sample proportions. Okay, so when I do that, okay, what that does is that I have a sample size of 100. Okay, I'm sampling according to that 0.26 and 0.74 breakdown. Okay, and then it's still random. So every time I might get, I don't know, like 25 versus 75, not exactly 26 versus 74, because that's what's in the population. But every time I take a new sample, I might have some variation going on. Okay, so this is how we're going to use the sample proportions in a second. Okay, so just to give you a heads up, okay? And the sample, we're gonna sample at random from the population, okay? So the population in our case. Once we do that, we're gonna return an array containing the distribution, okay, of the categories in the sample. So like I said, we're gonna put in the sample size, okay? We're also gonna do the population distribution according to the jury selection example is 26% versus 1 minus 26%, okay? And then this is still a random sample draw. So it's gonna give us the sampled proportions, okay, of the different categories. Okay. All right, so with all of this in mind, let's jump into this demo. Okay. All right, okay. So the population proportions, okay, so we're using what we call the model, right? The model is saying that there's no bias in the selection. So if that is the case, and we're going back to the population proportions, which is 26%, which is 0.26, and then 0.74. Okay, so they add up to 1, okay, and these are the proportions that we're sampling the sample from, okay? All right, now we are using the sample proportions method, okay, sample underscore proportions, okay, 100, like I said, is the sample size. So because the jury selection, the jury size is 100, so we put 100 in here. The population proportions, okay, this is what we defined earlier, 26%, and then 1 minus 26%. Okay, so let me show you. If I run this line, I will get an array. Okay, I will get an array of the breakdown of the proportions. Okay, in this particular case, I get 0.29 and 0.71. Okay, so this is saying that I am sampling according to the population proportions of 0.26 and 0.74. Okay, I am having a sample size of 100. Okay, and then this is giving me the breakdown in my sample of 29% and then 71%. Okay, to show you that this is a random process, if I do it one more time, oh, I guess I get the same thing by chance. Sorry, but then I do another time, I get 26%, 76%, 24%, 26, 76%. Okay, so I could keep doing this for many other times, but this is just to show you that we are sampling at random from this categorical distribution, okay, where we have the breakdown of 26% and 74%, which is the population model. Okay, make sense? Make sense? Yeah, so maybe let me just take a step back. The reason why we're doing this is that, remember, we're saying that when we're trying to approach assessment, okay, approach the assessment, what we're doing is that we can simulate data, right, according to the assumptions of the model, and then we can see how the predictions look. Okay, so just what we did in the demo really quick over here, right? The model tells us is 26% versus 74%, right, of the racial breakdown, okay? And then I can take simulate data out of it, okay? If I simulate once, I can see like 20% versus 80%, okay? I simulate another time, I get 28% versus 72%. So like the first value, you know, is the percentage. We know that it's percentage of the sampled being Black, okay? So if we are able to collect all of this in each of the simulation and multiply that by 100, we know the number of Blacks should be on the jury if the selection is purely at random according to the population breakdown of the race. Okay, so this is why we're doing here. Okay, we are using the sample underscore proportions method, a function over here. Okay, and we're sampling it according to the breakdown in the population. And then, as you will see soon, we're doing this for a large number of times, and then we're able to see how is the distribution of the number of Black men should be on the jury if there is no racial bias going on. Okay, so maybe we can now go to that point, and then we can revisit what we're trying to do. Okay, all right. So the sample proportions method, okay, down here, this is, we're wrapping it up right now into what we call panel underscore proportion. Okay, and what we do is we define this as a function, right? And then we run this sample underscores proportions. Okay, we run it, but we're only taking the first item because we are mostly interested about the percentage of the Black. Okay, so that's why we do the sample and then dot item parenthesis 0. Okay, because we're getting the first item. Okay. All right. So this is how the function is written. So if I run the function, now every time you see that I'm returning first percentage, right? And that's the percentage, oops, that's the percentage of black that we're able to get. Okay. All right. So this is only taking one. Okay. But like we're saying earlier, we want to simulate the data for a large number of times because every time we take a random sample, there's some random chance, right? We want to see overall, we want to capture that random chance across a large number of simulations. So we're able to know how our observed data lies in that particular framework. Okay. So to do that, okay, what we're doing, so I'm gonna slow down here. We are doing a for loop for 10,000 times, okay? Each time what we're doing, we are running this panel underscore proportion. So that gives us the first percentage, right, out of the sample draw that we have. So that's the percentage of black, okay? We multiply that by 100 just to show how many black men, right, out of 100 number person jury. And that's the every new draw that we get. And then of course we do the np.append. So we're able to have what we call a panels. Okay, so this, after we run this, let me set it to wrong. We should have 10,000 numbers of black men on a 100-person jury out of 10,000 times. Okay, and the jury selection, like we're saying here, because we're sampling each time we're sampling the proportion according to the population proportions, right? So every time we are simulating the data according to the model that there's no racial bias, okay? Because we're sampling it according to the population breakdown, okay? Now, okay, we can do a histogram, but maybe even before I do that, do you think 8 is something very likely to happen out of this 10,000 draws that I take? So if I go back to the problem before, okay, right? So 8 men out of 100 were observed. Okay, that's the observed data. Okay, the simulated data we haven't seen it yet, but you probably have seen all of the different checks that I did over here, right? So far, like 26% or 28%, and then I get another 28. I get another 26. So if I multiply that by 100, it's like 26, 28, right? Like sometimes 30, sometimes. So even just by doing this few number of simulations, we can see that 8 is very, very unlikely, right? Like it's, we don't know, like out of the 10,000 we're going to see in a second, but regardless, and I guess all of us, even by reading the question in the first place, was already a little bit suspicious, right? Like 26% of the population were black. How come you only have 8 men, right, on a 100-man jury? Okay, so your intuition is probably good enough, but here what we're trying to show is that, well, to assess that model, that if the model is saying that there's no racial bias going on in the jury selection, then we can always simulate data, right, according to the model, meaning that we're using the model to simulate data and then make predictions. And what we can do, so if we come back to the steps here, we can compare the predictions to the data that we are observed, okay? And we can compare them, and then we can tell whether the data and the model's predictions are consistent or not. If they're not consistent, then there's probably evidence against the model, right? If they're consistent, then we'll probably have evidence for the model, okay? So our intuition probably here is that, well, without even looking at that 10,000 simulations that we have done, this is already pretty extreme, that like a 26% breakdown, 26%, 74% breakdown, but you only have 8 men on a 100-man jury. That might be very unlikely to happen. Okay, so let's see if that is the case. Okay. All right, so this is 10,000 repetitions. Okay, we're using the bin from 5-ish to 40. Okay, and I will pause here for a sec so you can take a look at this histogram a little bit. Okay, I guess there are 2 main questions to be answered here and for you to think about. One is that, well, the distribution does seem to be a little bit symmetric, right? So where it is centered on, that's my first question, okay? The second one, why? What do you think why that is the case? The other one will be, is 8 something very likely to happen? Okay, so that's my questions for you all. And let me pause recording. Okay. All right. I guess, yeah, my two-part question, if you remember, where does this distribution center at? And that's part one, and why? The second part is 8 a likely value out of the simulated data that we're seeing over here? So any thoughts? Feel free to
It's
speak.
centered around like 25 or 26, and 8 is not an expected value.
Yeah,
it's very much on the side.
Yeah, exactly. Okay, and thank you. I think that's Sha, and then thank you, Lance and Samantha in the chat as well. Yeah, so the center I think is around 26, and also it's probably not very surprising, right? Because we know that 26% of the population is Black, and then that's the population distribution that we're using, right? Population, I guess, proportions over there that we use to simulate. So it's not surprising that it's going to center at that. But then, of course, we have some variability going on, right? You can, in the 10,000 simulations that we have done, you can go as low as, I don't know, 14 maybe, and as high as 40, okay? However, 8 is far away, I guess, from the lowest number, which is 13, okay? And that tells us something, right? Like say, we have done a large number of simulations, okay, using the model. Okay? And the model, again, is saying that there's no racial bias, okay? So we are simulating the data according to the racial breakdown in the population. And that's what the model is saying, okay? And we do that for a large number of times. We notice that it's centered around that 26% or 26 out of the, if the unit is the number of people. And then 8 is very unlikely to happen. In this case, actually 0 chance of happening, because every possible values that we have seen so far is greater than 8, okay? So that can tell us, well, something is probably like, that's actually, so if I come back to the slide really quick over here, okay? Remember, we're saying that if the data and the model's predictions are not consistent, just like what we're seeing over here, 8 is the observed, okay? The model predictions is that histogram, okay? Then there is evidence against the model, okay? And for our case, this is pretty extreme because 8 doesn't appear any time, no time that we have seen it out of 10,000 simulations that we have seen this. So that's probably telling us it's very unlikely. And soonish, we're gonna see that how we can actually compute, and you probably have heard about the term before, p-value. Okay, that's the probability of observing something as extreme as your data, given that the model is correct. Okay, so remember what we're doing here is that we're simulating the data according to the model where there's no racial bias, right? And then we have simulated the data. This is the histogram showing it. And later you will see that we're able to compute what we call p-value. And in this case, the p-value is 0. Like there's no chance they're going to observe something as extreme as 8, okay? If you think there's no racial bias. And then that is what we call p-value, and that can be a decision-making tool, okay? In terms of whether we think the model assessment is passing or not, okay? All right, I think we're running out of time, so feel free to log off, but I would just say that whenever you have questions, definitely feel free to type in the chat privately or just to everybody, and I can always slow down. So I think that's probably the best way for everybody to keep on the same page whenever you have questions, so we don't let it slip, and then hopefully no more new questions accumulating along the way, okay? All right.
Thank you.
Thank you.
Take care.
Are we gonna have some homework this week?
Yeah, I think we are trying to release the homework for what is due next week. Later on, yeah, like I think like by Thursday-ish. Yeah, so we are not having nothing due this week, just to, I guess, everybody should catch up a little bit. And then, yeah, so good question. I don't think we have anything due this week.
Okay.
Yeah. All right. Take care. Thank you, Juliana.
Hello everyone, welcome to this short video to give you an idea of how you can work on your group project. In particular, we want to show you how you can download the data sets from various sources that we post to the Moodle. And then once you have downloaded the CSV file, how you can upload it to your workspace so you can work on it with your Jupyter notebook, okay? So this is a sample final group project, and you're gonna fill in all of the details by answering those part of the questions and all that. And what I want to show you here is we're gonna show how you can, like you're gonna write about your research question, of course, details about your data, And then we're gonna show you where you're gonna load your data later on. Okay, so if you go to Moodle, you will see that in our course site. On our course site, we started to populate this climate data sources section. Okay, so we throw in a lot of material we have found, but of course, you're always able to find the other ones that you want. And just to give you a demonstration, I'm going to try to look at this emission indicator data source. Okay, so if you click that data portal, you will see that this is a, this website is called Climate Action Tracker. Okay, and you will see that you can download different source data, of course. And in particular, for this data, for this portal, what they asking you to do before you can actually get the data, I think, is that you will select a particular country or region. So for demonstration, let's select EU, and let's do electricity, okay? And let's do electricity activity per capita, for example. And you can choose more, as you can see, okay? So maybe for demonstration purpose, I'm going to choose two different indicator. And let me actually just add one more sector there as well, okay? And scenario, let's just see. So you can do historical data. You can do projected current policy. For demonstration, I'm going to choose historic data, okay? Once you have chosen all of this, you realize that they do a really nice line graph for you, okay? But for our purpose, of course, we not only just want to visualize the data, but we also want to work with the data to perform, for example, hypothesis testing, etc., etc. So for our purpose, let's download the data. And once you click that, you realize that they have three different ways that you can get the data. For us, always try to get the CSV file. Okay, so you can see that it is one of the options here. On the other data sets websites, make sure that when you explore, and once you have selected all of the ones that you want, make sure that you download the CSV file. Okay, so if you now go to, once you do the download, you'll realize that is in your downloads. Okay, in my downloads at least. Okay, so for you, now you can come back to your Jupyter Notebook space. Okay, and you click this Jupyter, and you will see that you will have this project folder, right? You have the individual, which is the quiz 2 replacement, and you will always also have your final. So what you can do here is to click the upload. We did this once before the break, okay? And let's just click the data that we selected, okay? And just to help you to navigate, you realize that we typically try to eliminate space, okay? In the data set name, okay, in case later we want to use them, okay. So make sure that you can either add it in the way that I did just now, or you can click it and then rename it, okay. So for example, I can come back and rename it, and maybe I don't want the space anymore. I don't want the underline, for example, so I can do the rename. Okay, so now the data is in your workspace, okay. So what you can do now, as you know, we have done this many, many times, right? So you go to where you're going to load your data. Let me close this. Okay. And then, so for example, I'm going to load my data as what? Table.think, right? What was it? I might not be able to get it. Give me a second. I just want to take a look. I guess, as you can see, you can always cheat based on, I know, I'm kidding, not cheating, but check out what you have done before to see what you can do, okay? So for example, if I click my individual project, we're not showing you how to do things, of course, but I guess just to get a sense of like a quick cheat sheet that we can do. This is a little slow, sorry about that, okay. So I just want to see how to load the data. I want to make sure. Okay, it's table read table. Okay, so my bad. I should have prepped that. And then you have to supply the name of the data set, which in our case is European Union data, right? Okay, so you can put it over here. Okay, and then let's take a look at part of the data. Okay. and then you can see, okay. So remember we selected 2 sectors, I think, and then 2 indicators. So you will see that we have the electricity and the electricity activity, but I'm sure like you see that some of the rows are omitted. So as you keep going forward, you will see the other sector. I already forgot what I chose, but you know what I mean. And then the other indicator, okay? And for country, I think we only select EU, right? But if you want to do multiple countries comparison, you can select, or regions, I should say. You can select multiple if you go back to the data, right? Remember, oh yeah, we selected electricity and buildings and then those 2 indicators. So, okay, okay. Right, so this is compare indicators. I guess if you go to this, you can select multiple country and region, and then you can do a comparison over there if that's what you want to do, okay? So, all right, so I think this gives you a quick overview of what you can do. But again, there are many different data sources that we posted. Feel free to explore them. Also, feel free to go to the other sources that interest you more. The key here is at the end of the day, when you download your data set, you want to make sure that it's a CSV file. Okay, so you are able to later upload it to your workspace to work on that with your Jupyter notebook. And also make sure that you know what each variable is about. Okay, so like what is the sector, what is the indicator, and say scenario and country, and all of this information should be accessible. If you go back to the website that you found your data, try to make sure that you know what each variable is talking about, of course, right? And what are each levels about. And because that will also go into your final project write-up that you're going to talk about your data source, data collection, what are the variables, the type of study, etc., etc. Okay? All right, so I hope you find this useful, and always feel free to reach out to us if you have any questions or concerns, and we look forward to reading your project.
All right, welcome back. Happy Thursday. So I want to kind of pick up where we left off last time, and I want to talk about this idea of when we come up with a model. So the idea that we've gone so far is we have some data and we want to come up with a model for that. And then when we've come up with a model for that data, then we want to figure out what are the steps where we can actually assess that model and see if it's valid or not. And this will kind of turn into kind of a general framework that we're going to follow for many different examples for different types of models of the data. But it comes down to coming up with a statistic that will help you decide whether your data, whether the data supports that model or something else, right? So the question we're asking is, does the data support our specific model? And we want to choose a statistic, and the statistic we choose is up to us, but the statistic is important to pick one that would actually support the model or some alternate view of the world if that statistic doesn't support the model. And so once we've come up with that statistic, then what we're going to do is we're going to simulate under the assumptions of the model. So, and we'll look at a specific example in a second, but we're going to simulate that statistic, and then we're going to look at the distribution of those simulated values. And this is our model. This is our prediction of how that model is going to bear out. And then we can look at our observation and see where it lies on that distribution. And that should tell us whether that particular distribution, the observed statistic, right? So the observed statistic is the thing that exists in the world. That is the thing, the actual statistic that we're comparing to our model. And if we look at that observed statistic and see where it kind of falls in our histogram, our distribution of simulations, that will give us an idea whether a model was valid or not with that, in particular with that observed statistic. Okay, so let's look at a specific example. And we're going to go back to Gregor Mendel, and He was a monk that was really into gardening and is also and running experiments and doing observations. And he's kind of known as the father of genetics. And one of his famous study was he raised a lot of pea plants. And in particular, his model was, and they didn't know much about genetics and about dominant and recessive traits at that point, but he was growing these pea plants of a particular kind. They had two types of flowers. They either had purple or white flowers. And his model was that the chance of when you planted these pea plants, there was a 75% chance that the plant would be purple flowering, and a 25%, and regardless, so the purple, regardless of the colors of the other plants. And then what we want to know is that model good enough? And of course, we know kind of now about dominant and recessive genes, that we know we have an explanation, a biological explanation for this model. And this model turns out to be true, is that purple is a dominant gene, and the white flower is a recessive gene. But they didn't know any of that at the time. And so let's assume that we didn't know that the model is valid. Can we use simulation to verify what he was seeing, or that his view of the data is accurate? Okay. And so before we kind of look at this example, I want to take a moment and I want you to think about kind of how would you assess this model? And so we kind of know the general framework, kind of what we've talked about, but in particular, what statistic would you use? And so let me pause the video here. Okay, so let's talk about how we would assess this model. And again, the framework for kind of looking at the model is that once we've come up with our statistic, we're going to run a bunch of simulations and display the histogram and then see where our observed statistic falls in there. And so really kind of when we talk about assessing this model, it comes down to what statistic are we going to pick? And so for this particular instance, really kind of the key statistic here is, and because we're comparing to these purple flowering plants, we really are interested in how much deviation are we around, or are we away? And what I mean by deviation, how much smaller or larger than we are from that 75%, okay? And so a good statistic for that would be the distance away from 75% from there. And so, and that's simply, right, the distance is simply the percent that we get of the purple flowering plants minus 75, and we're going to take, because we care about the deviation from that model, not whether it's necessarily larger or smaller. We want to know in particular just how far away is it from 75%. So we'll take the absolute value of that, and that's just a standard distance metric from there. And the idea here is that now, so that's it, the statistic is the difference from 75. And so the idea here is that if the model was, if the zero would mean that there's no deviation. If the statistic, the larger the statistic gets, and because we're doing distance, it's not going to be minus, it's going to be a positive number. The larger the statistics, that is more evidence against the model. And so let's take a look at that. And we can run this. We can run this simulation. Okay, and so we just kind of have our boilerplate code up here. And then, so first, now we want to go back and here, let me just clear out all the output here. And now, because we want to recreate Mendel's experiment, we want to look at the observed percentage. And so when he did his experiment, he grew 929 plants. That's a lot of plants. That's almost 1,000 plants. And 709 of them had purple flowers. Okay, so the actual observed percentage is going to be 709 over 929. Okay, and so he observed about 76.3%. Okay, And so now what we want to do now is we want to run our simulation. So we have our observed value, and now let's get our setup for taking our sample. And because we want to reproduce the experiment, what we're going to do is that and we predict our model is going to be that we'll get a purple plant 75% of the time, 0.75, and something else, a white flower, 0.25 or 25%. Okay, so what we're and because we want to reproduce that experiment, we want to run our sample proportion. And remember, that's just going to pick randomly from our predicted proportions in that actual proportion from there. And so that's going to give us the total number of percentage for a particular trial, right? So the thing to remember is that this is one statistic from one simulation. And when we run it, because it's random, every time we run it, we're going to get a different value. And if you can see, we do that. If I run it, we're going to get slightly different values each time. Okay. So then what we want to do is we're going to define a function to run this and actually give us the number of purple flowers. So that is just running using our sample proportion. And if you remember, as we can see from above, that returns an array. And the thing that we're interested in is the number of purple flowers. And so we're going to grab the first item of that array. So item 0 is going to grab this item here, which is the percentage. And if we want the actual number, if we want the number of flowers, we want to turn that percentage into a number of flowers, we're going to multiply that by 100. Okay. So now we have that function, and then every time we do that, we'll get some number of flowers out of that. Okay. So now that we have our statistic, we have our function that generates our statistic, which would give us the number of purple flowers. Now we can run our simulation. And this is the framework that we're going to come back to time and time again. So it's worth spending a couple moments and talking about exactly what's going on. And so in computer science speak, this is actually kind of a design pattern. It's called an accumulator pattern. And how that works is that we're going to initialize some value outside of the loop. And this is going to be our initial value. And in this case, what we're doing is that purples is going to be an array of observations. And so we're going to initialize it to some initial value. In this case, it's an empty array because we haven't seen any observations yet. And so purple is going to be our accumulator variable. We're going to save that. That is going to be the name. We're going to store all of our results. And so we need to initialize it, give it some initial value outside of the loop. And so then we have a loop here, and this for loop is just, we're going to do a for loop just to run the simulation a certain number of times. For this example, we're going to run it 10,000 times. And then in the body of our loop, we're going to get the value that we want. And so here we're going to get the new purple. And then what we're going to do is we're going to accumulate that result. We're going to add it to the array. And so this line here, this new purple is going to give us a new statistic from our experiment. And then this line here, what's going on here is that we're going to add it to our purple array. And so we're working in the confines of the NumPy append function. And what that does is that takes in an array. And so we're passing in the array. The second argument is the new value to add to the array. And then what it does is it actually returns a brand new array. It returns an entirely new array with the new value, in this case, new purple, added to the purple array. And so because the NP append, the NumPy append, returns a new array, we have to reassign it back to our purple array. Okay. If we didn't do that, that value that gets returned from this function would get lost. And so this is kind of a paradigm, and we'll see this kind of again and again. And so that's kind of what's going on. You can just remember it, but this is the way that we add in, this is the way that we add a new value to the purple array. Okay, so we're passing in the array in and the new value, and we're getting a whole new array, which then we assign back to purple. And so at the end of that, at the end, when we run this loop, purples is now going to be an array with our observations, and it's going to have one observation for every time we ran in the loop from there. Okay. Any questions about that, how that works? Because this is the basic framework for us doing our simulation. We're going to come up with a statistic. We're going to initialize our accumulator name. In this case, we called it purple. We're gonna simulate n number of times where n is some large number. And we'll talk about later in the course, like what is large enough, right? Right now we've been vague. We've just said we just run this a large number of times. We'll get more precise about what exactly is large enough. But for now, just we're going to run this many times, and then once we have that array, then we can display a histogram of that. And to display the histogram, we got to turn that array back into a table. And so this is where this line is coming from here, right? So we're taking, right, so if we just look at purples, we can see it's an array. And then if we got the length of that, you can see it should have 10,000 observations in it, right? But if we want to see them, we have to convert them into a table. And so that's exactly what we're doing here. So the table, this will create a brand new table for us, an empty table with no values. And then we're just saying we're going to take that brand new created table, we're going to add the column, and then we'll give it a name, and then the array for that. So this is now going to give us a table. And then not shown here, just on the end there, we're going to display that into a histogram, right? If we did that, if we just left that off, we would just get the table. And so now this is the distribution of the flowers that we got from this. And you can see it falls very, very much in line with our prediction, where we would expect about 75 flowers in our sample. And so again, right, so what we're doing, we took a sample of 729, we looked at the number of, we got the percentage of them that were purple, and then we multiplied by 100 to get an integer, to get the actual number 75 from there. Okay, and so then now what we can do is we can look at the different from the statistic. Okay, so what we're doing here is, again, we're just going to look at another table, and we're just taking the difference now, right? So this is just giving us the number. This is not our, this is the number. This is not quite our statistic yet. Our statistic is the distance away from 75. And so we calculate the distance by taking the purples minus 75, that 75 we got from our model, and take the absolute value of that. That will give us the actual statistic, okay? And if we expected the model to be accurate, we would expect a low discrepancy. And that's exactly what we see, right? For many of the trials, there was, it was very close to zero. It was very close to, it was so a distance of zero means that it was very close to 75. And you can see it kind of trails off from there. And now if we actually look at our, so that's the distribution, right? So so what we've seen is this is what we would expect to get from distances away from 75 if due to random chance. And so now we can look at our observed value and see where it falls in that distribution. And if we look at what Gregor Mendel actually observed, we'll see that we get about 1.3. And so where would that come on this graph? This would come at this graph somewhere around here. Whoops, somewhere where my arrow is from there. And you can see that's kind of well within what we would expect due to normal process. And so we would say that the simulation supports the model that 75% of the flowers are purple. Any questions about that? Okay. Very good. Okay, then we will kind of move on from there. And so kind of along this same theme, of figuring out kind of choosing statistics, for both A and B, what I want you to do is choose the statistics that will help you kind of choose between the two viewpoints. So like the viewpoint for A is, so imagine our data is, we have the data of 400 tosses of a coin. So flip a coin, heads or tails. We've collected the result for 400 trials. And so that's the data. And you want to kind of think about a statistic that would answer the question in the case of A is this coin fair? Is this coin fair? Yes or no, it's not. Okay, so that would be kind of what would be a statistic for that. And then for the other scenario B, the coin is fair, no, it's biased towards heads. Okay, so the first one is just saying whether it's fair or not. The second one is asking a more specific question. If we're asking if it is biased towards heads from there. And so take a moment, I'll send you back into your breakout rooms, and then take a moment to think about what the statistics for the statistic for A would be and for B, and are they different? And if they are, how are they different? Any questions about the discussion before I send you off into the breakout rooms? Okay. All right. I'll see you in a moment. All right. So before we come up with a statistic, we want to think about what does it mean to be fair? Okay. And so in this case, we should define kind of what we think of as fair. And so if we're given 400 coin tosses, if we got 200 heads, that would suggest a fair coin. Okay, so, and that's kind of for both cases, A and B, right? A fair coin you would expect with 400 tosses, because half of the times it would come up heads, half the time it would come up tails. We would expect 200 heads would be fair. And so we can use that when formulating our statistic. And so for the first question, A, right, where we're answering the question of not fair, anything that's very large or very small away from the number of coin flips would be an indication of not fair. And so here is a good candidate where distance would make a lot of sense. And so a reasonable statistic for case A is using the distance between the number of heads we get in our trial and 200. And so what would that actually look like? Again, it would be the absolute value of the number of heads minus 200. And the idea here is that the larger the statistic, the more not fair the coin would appear. Okay. And so because we didn't care about whether, because we just were really cared about not fair, we didn't care in the formulation of A, we didn't care if it was biased towards head or biased towards tails. We were really just answering the question of not fair. And so any deviation, either smaller or larger, would be a representation of not fair. But in the case of B, we really were asking a more specific question. And so the idea here is the number of heads would suggest kind of some form of bias towards heads. So the statistic here might be actually just not looking at the distance metric, but looking at the number of heads and seeing if it's, greater than or smaller than. And I think you'd also make the argument, subtracting from 0, right? That doesn't really change anything. It just changes the offset from there. So if you were coming up with a statistic of the number of heads minus 200 without the absolute value, I think that makes a lot of sense as well. So do you have any questions? Did you come up with any statistics that were significantly different than what I just talked about? Conversely, do you have any questions about how I picked those particular statistics? Okay, so I will take that as this makes sense. And so fantastic.